Welcome to the part 1 of lecture 5. In this lecture, we will focus on nice applications of regression model in time series data. Time series data is ubiquitous in data science. As a data scientist, when you will work in corporate sector or academia, almost every project or the problem that you will see, almost 80 to 90% data will have some kind of time component and will be treated as a time series data. Regression model is one of the most commonly used statistical tools for forecasting time series data. There are two kinds of forecasting that you will typically do when from a time series data. One is typically known as long-term forecasting, another typically known as short-term forecasting. In long-term forecasting, we try to model the trend in the data and the seasonality of the data as a function of time. If we can model the trend and seasonality of data as a function of time, then it helps us to forecast long-term horizon. However, in the short-term forecasting, we use a very different strategy. Typically, we try to resort to a detrending of the data, and from there, what we try to do, we use the recent historical data to forecast the recent future in short-term horizon, with the hope that in the recent historical data and the recent future data will be reasonably correlated. Therefore, if we use the recent historical data or recent past data to forecast the recent future, then our short-term forecasting will have a greater accuracy. First, we will focus on long-term forecasting with trend. In this lecture, throughout we will consider a very popular time series dataset in the data science community called AirPassengers dataset. The dataset spans from 1949 to 1961. Over these years, how air passengers in the United States, number of air passengers in the United States in million has increased significantly over the years. We can clearly see that the data has a very strong upward trend with a clear annual seasonality, and also that seasonality is very strong seasonality. What we will do this in this particular data set, we split the data set from 1949 to 1956 as our train data set. We marked it with purple color, and this dataset we will consider as a train dataset. We will fit our model with only this data, and then we will try to forecast the from 1957 to 1961, these 4 years we will try to forecast, and then we will check how good our forecast is, and we will try to forecast both the long term as well as the short term strategy to forecast these 4 years of data. You can model the trend of air passengers dataset as a linear function of time or quadratic function of time. In this lecture, I modeled the trend of air passengers as linear function of time. However, I encourage you to model the trend of air passengers as quadratic function of time and check whether how good or bad the performance is. And when you try this kind of deviations, then only you will learn how a particular model works in terms of accuracy in the out of the sample data forecasting. Suppose Y sub t is the number of monthly total of international airline passengers from the time point 1949 to 1960. The linear trend we are going to fit as yt equal to beta naught plus beta 1 times t plus epsilon t. Now, what is the data structure that we have in the data train? What we have y these values and time is these values. Now 1949.000 is actually represent the month of January of 1949, where the 0.083 represents the month of February of 1949 and 0.167 represents the March of 1949. And these are the number of air passengers that traveled during that month of that year. So this is typically the data structure that we have, and we have to fit this model in this data. Linear model for y equal to x beta plus epsilon, we can consider this linear trained model in this structure where y is y1 y2 yn and x is 1 1 1 on the first column, which corresponds to the intercept parameter, and t1 t2 tn corresponds to the second part, the beta 1 times t, and the beta corresponds to beta naught comma beta 1, and the epsilon corresponds to epsilon 1 epsilon 2 epsilon n. Now remember that when I implemented this model, I scaled the time, and that kind of helps me to convergence and give the nice results. So these are the estimates, and these are the standard deviations. T value and p value is too big and the p values are too small. Adjusted R square is 0.816. So it indicates that trend alone can explain the about 82% of the variability of the air passenger dataset. So I took the data, I fit on the training data, then forecasted. This red dash line is the forecasted values, and these are the original values. So clearly, if you just use trend, you will get the overall trend, but you will miss the entire seasonality part. So you have to next model the seasonality. What I did, I calculate the residuals after trending and plot them. Sometimes this kind of residuals for the strong time series data which has a strong trend are called detrended residuals. Now clearly these residuals are actually what is depicted is the seasonality. So now we have to model the seasonality on the residuals. What I did, I modeled the residuals RT as equal to alpha naught plus alpha 1 times sine omega t plus gamma 1 cos omega t, where omega is 2 pi by 12. But 12 is for 12 months. Remember that my data is monthly, and this each of these seasonal behavior, if you look at here, this is 1 year typically. If you start look at from here, this corresponds to 1954. So now this is one season, like it is somewhere in the 1955, and then another season is somewhere in the 1956, then another season somewhere in the 1957. When we model this, it looks like a sinusoidal behavior, and it's nicely behave models the seasonality. But still these jumps, ups and downs are not getting modeled nicely. So what I did is I went up to the second Fourier. These are sometimes called the Fourier transform also. The sine omega t cos omega t are also sometimes called Fourier transform of the time or the time domain. I went now up to the second Fourier where alpha 1 sine omega t, and then I took alpha 2 sine 2 omega t, and gamma 1 cos omega t, and I took gamma 2 cos 2 omega t. Omega is 2 pi by 12. I know the exact value of omega, so I know the exact value of sine omega t. Similarly, cos omega t or sine 2 omega t or cos 2 omega t. So effectively this is, I can fit it as a simple linear regression model, and turns out now it is modeling slightly better. The You see there is a this nice pattern is getting modeled nicely, but still it cannot model the jumps. These jumps still cannot be modeled, and in the beginning it is underestimating, and in the end of the training dataset it is overestimating. Now I'm going to fit the model with both with the trend and the seasonality. So alpha plus beta t is going to model the trend, and alpha 1 plus sine omega t gamma 1 times cos omega t plus alpha 2 times sine 2 omega t plus cos 2 times plus gamma 2 times cos 2 omega t. These are all going to model my seasonality, and omega is 2 pi by 12, so I know all these Fourier transforms or engineered features or Fourier features. Now in this model, the purple is my actual original data and the red ones are the fitted data from the training dataset, and then we use the prediction to forecast ahead for the next 4 years, and then we plot the original values. So clearly it picks up the trend, it does pick up the seasonality also to a great extent, but it completely misses the jumps. It cannot model the jumps. So the problem, so now the question is, how can we model the jumps? Looks like the jumps are increasing at almost at exponential rate. Just visual experience tells me so, but we will see how can we do that, how can we model that. Now one way of doing it, we can model the y as a log. We can take a log transformation of the y or the AirPassengers data set, and rest of the trend and seasonality part stays exactly same. If we model it in this way, so previously we were modeling yt directly as a function of trend plus seasonality plus some white noise. Now we are modeling it as a log y plus trend equal to trend plus seasonality plus white noise. Now if we do that, it looks like it does slightly better than the you know previously. And now this is my forecasted path of the air passenger demand, and this is the original. The blue ones are the originals and the green ones are the forecasted path. Now this is slightly overestimations are happening, but overall it has nicely fitted the jumps by as a log transformations of the model. So this is a nice applications of simple linear regression in modeling time series to apply it in the long term forecasting. So I can effectively, I on the December of 1956, I can effectively forecast for the entire next 4 years how the demand will be. And interestingly, what we see that the demand almost mimicking the is going through the forecasted path, except for a couple of months we see some underestimation is happening. I am sure if you try to model the seasonality, I have modeled the seasonality up to second Fourier. If you try to model the seasonality with 4 or 5 or 6 Fourier transformations, I'm pretty sure you will be able to cover this underestimation, and it will be almost no, I mean, estimate this underestimation will be, or overestimation rather, will be corrected. Now we will move on to short-term forecasting, and typically for the short-term forecasting we rely on autoregressive model. How the autoregressive models works, let's look into the, so we have to, in order to fit the autoregressive model, we have to create the data structure with lag variables. So how the things work, so suppose this is actual the original data, t1 y1, t2 y2, t3 y3, tn yn. Now how the lag variables will work. So if I'm on the second row, t2 y2, what is the lag variable of y2? Lag variable of y2 is y1, so I just bring it here. I create a third column and say that, well, the lag variable, one lag variable of y2 is y1. Similarly, if it is t3 y3, then the one lag variable of the y3 will be y2. In this way, up to n, the last value we will check, tn, the time point nth time point, we will say that yn is the value, and the n minus 1th lag variable is yn minus 1. Now this is how we will write it down. So here is the time, here is the y. Now 112 has come down here for the y lag 1. So this is the lag y1 column. 118 is here, 132 is here, 129 is here. So 129 is the lag value of the 121. 121 is the lag value of the 135. That's how we create the data structure for autoregressive model. Next, we define another variable called first difference of yt in log scale. How we define first difference of yt in the log scale? So delta yt we define as the first difference of yt in log scale, which is ln yt minus ln yt minus 1. If you look it carefully, basically it is you take the log of y and then you take the consecutive difference of the log y values. This is also known as the log return in quantitative finance. We are using that same log return concept here as well. So other than this thing, we also calculate the first difference of the yt in the log scale and its lag values also we create it. Okay. Now we have these lag values. We put these y lag 1 values on the x-axis and the original y values on the y-axis, and that's what we see. So this is the lag y values and this is the original y values, and what we see is there is a clear cut straight line relationship between today's value and the tomorrow's value, or yesterday's value with the today's value. But as the value increases, we see that the variability increases, but that the lower value, the variability is much less. So we fit a autoregressive model of order 1, which is yt equal to beta naught plus beta 1 yt minus 1 plus epsilon t. When we fit that model, this is the intercept model, and this is the intercept of the model, and this is the coefficient corresponds to the So this is beta naught, this is beta 1. This is the standard errors. These are the t values, and the p value is very small. So of course the beta 1 will be significant. But we did a Brush-Pagan test to check the homoscedasticity, because we see the variability is much higher and variability is much lower here. So that indicate that most probably the data here is heteroscedastic. Now when we do the Brush-Pagan test, what we see that p-value is extremely small after decimal 6 zeros and then 6658. So under the light of the data, we can reject the null hypothesis, where null hypothesis says that it is homoscedastic, and it says that no, it is not homoscedastic, so it is actually heteroscedastic dataset. So we took the log transformation, so ln yt minus 1 and ln yt, and then we plot them. Now you see the variability here and variability here is almost same. Now if you fit the model log of yt equal to beta naught plus beta 1 log of yt minus 1 plus epsilon t, we see that coefficient does not change much. You look into this here, 0.945, and still it is 943, whereas if you look into the intercept has now come down to 0.312, whereas both of them are almost significant, but the p-value is now 0.8204. So that means we fail to reject the null hypothesis that it is homoscedasticity. So the residuals are homoscedastic if we do take log transformations. So this is a very good news. Then we plot the residuals over the time, and clearly the residuals have some seasonality, we can clearly see. And you can try some seasonality, the Fourier transformation, to model these seasonality in the residuals as well. Next, what I'm going to do, we are going to, you remember that we took the first difference of the log y values. So I decided to plot the lag of the first difference of log values and the original value itself. What we see a very interesting geometric pattern. So we see that there is a hole in the point cloud, sort of a hole. So it's typically called the torus kind of behavior. Torus is on the 3D, but here it is more like a torus in a 2D. you know this is very rare thing we see, and now this kind of topology you will generally won't see in the typical time data sets, typical data science data sets, but these are the data sets that are very commonly interested in something called a very new emerging area is coming out called topological data analysis, which interested in the topology of the data. And this is a particular topology where a hole exists inside the data points or the point clouds. After fitting the log transformed values, we fit the fitted values versus residuals, and we can see almost there is no you know pattern in the data, and that's a very good news. It tells us that, well, there is nothing is happening, so that maybe that autoregressive model with the log transformation is the right model to work on. So we took the original data set, that this is the training data set, and on the training data set we fitted the model, and model fits almost accurately on the data set. So it's a very good fitted model. And then we fit the one step ahead forecast using that autoregressive order 1 model, AR1 model also known as sometimes, and it does a reasonably good job in terms of forecasting, just one step ahead. It cannot do a long-term forecasting or any sort of things. Other time series models which are very popular in the time series data analysis, such as ARIMA model or Kirch model or state space dynamic model or spectral analysis model, etc. These are typically very non-linear in parameters, so we cannot directly apply linear regression type models. So, and also these models are effectively not part of this course. I just showed you that how a simple regression model can be effectively used in modeling long-term forecast and the short-term forecast of a time series data. In the next part, we will discuss another nice application of regression model known as grandeur causality model. Thank you very much. Please keep watching. Take care.